All right, so we're finishing up student activity sheet 10 today. And what the objective for today is we are taking what we've been doing with the map coloring and how we relate it to graphs, and now we're going to use that to solve problems dealing with scheduling problems, which seems unconnected, but it turns out that this is a handy thing to be able to do. Okay, so hang on for that. Here it comes. Hey there, we are going to finish up activity sheet 10 today. What we're going to do today, yesterday we looked at how maps and graphs were related, and today we're going to actually use this process using map coloring and graphs as a way to help with scheduling problems, and so we'll see that later on in this lesson. All right, I want to backtrack to just the last few problems that we looked at yesterday. First thing was number 5. We did 5, 6, and 7 to finish up the day. Number 5 asked what types of graphs can always be colored with two colors. And I kind of hinted at this on number 4, but one type, trees or graphs with no cycles, which are the same thing. You know, you have a graph with no cycle, then that's also called a tree. And so those you can get by with two colors. Or any kind of polygon, which is a closed figure with an even number of sides. So a rectangle, a hexagon, an octagon, a decagon, you know, 2, 4, 6, 8, 10, any of those you can get by with two colors. Once you have an odd number like a triangle, well then you're going to need 3 colors. Or a pentagon, you would have to have 3 colors. All right. Number 6 asks you to create a graph that needs 5 colors and then draw the associated map. So here's my graph that needs 5 colors. I have 5 vertices, so 5 regions, and every region touches every other region, right? They all share a common border. The problem is I cannot draw a map from this. In fact, it's impossible. Every map can be colored with 4 colors. So I was a little bit mean to you. I left you twisting the wind there a little bit when I asked you on the previous lesson on Student Activity Sheet 9, I asked you to try to make a 5-color map. Well, you can't do it. There's no such thing as a map that needs 5 colors. The most you ever need is 4. Okay? I can make a graph that needs 5 colors. This graph would need 5 colors, but I cannot draw a map that fits that graph. All right? So that leads us to number 7. Number 7 says, when might a graph not correspond to a map? And if anybody came up with this, I'll be very, very impressed. But right now I have this is going to be a situation. This would need 4 colors, right? And I could just maybe start with 1. I could say this needs color A, and that has to be different. Region B needs, you know, color B here, color C here for 3, because that makes a triangle. They all have to be different, all right? Here 4, it's connected to 1, it's connected to 3. It's also connected to 2 by this loop outside, so that would need a different color. I'm going to put that D. But 5 here, 5 could be the same color. It's connected to 1 and to 2 and to 4, but it's not connected to 3, so I can make 5 color C as well. If I tried to connect those two, the only way I could do that is by to cross some line I already have. Okay, so here's the thing. If you can draw a graph with no intersecting lines, then you can draw a map that goes with it. As soon as you have to intersect a line, cross a line to draw the map, to draw the graph, then you cannot draw a map with that. Okay? So this dashed line, if I added that dashed line, then I can no longer make a map that goes along with that graph. All right. So having said all that, let's get on to today. So first thing is number 8 here, talking about a chromatic number. So we'll be talking about chromatic numbers quite a bit here. The chromatic number of a graph is the minimum number of colors needed to color each vertex in such a way that any 2 vertices sharing an edge are a different color. Provide examples of graphs that have chromatic numbers of 3 and 4. 3 and 4. So 2 different graphs, one needs 3, one needs 4. So it's the minimum number. All right, it's the minimum number. If you can get by with 2 colors on a graph, then that graph has a chromatic number of 2. If you have to have 3 colors, then it's going to be a chromatic number of 3. If you have to have 4 colors, it's going to be a chromatic number of 4. And realize, you know, with a graph at least, we can have more than 4 colors. If it's a map, we'll never have more than 4 colors, but we can have a graph with more than 4 colors. All right, I'm going to pause the video, let you try to come up with graphs for 3 and 4 here, and we'll come back and talk about it. Okay, so chromatic number 3, let's go back to our trusty old triangle. If I have a triangle, that needs 3 different colors. I color this one color A, color B, and then this point has to be different from B and different from A, so it could be color C. That would be a chromatic number of 3 for that. All right. Same thing, if I want chromatic number 4, I can have 4 points that are all connected to each other. All right, so let's see what that looks like. So all of these are connected to each other this way. So, and then I could draw a diagonal across here to connect those two. Everything's connected except for this point, and I could just kind of loop around to connect those together, and nothing's still crossing each other. So A has to be different from this point B. B has to be different from both of those C, and this one has to be different from all 3 D. So that would need 4 different colors here. Okay, yeah, you could certainly do more complicated things that would need 3 or 4, but this would get the job done. Number 9. Give an example of a graph with 20 vertices that has a chromatic number of 2. Does your graph have any cycles? Recall, a cycle is a path through the graph that starts and ends at the same vertex, does not reuse any edges. Okay, so see if you can come up with a graph, then decide whether it has a cycle or not. All right, pause the video, let you work on that. Okay, so 20 vertices, chromatic number of 2. So I've drawn 2 sets of 20 vertices here. So one way, we know that if you have a tree, no cycles, you can do that with 2 colors. So I could just make that this situation. You know, I could just connect this and have no cycles in it. And I could have 20 points all connected together, but nothing ever loops back. And so I could get by where all the points on the top row are maybe color A, all these up here are colored A, and all the ones on the bottom are colored B, and so I could get by with 2 colors there. We also know that a polygon with even number of vertices, or even number of sides, also you can get by with 2 colors. So I could just make a polygon here. I could connect all these points, and then I could come down here and I connect all these points. And then I could connect this, and so I could just alternate. A, B, A, B, A, B, etc. all the way around. And notice B back to A again. Okay? All right. So here's now how we're going to use this. We're going to use this in what's called a scheduling problem here. So Mrs. Jacobs, the new principal at Riverdale High School, wants to make a good impression by offering a lot of new exciting classes for her students. The principal plans to use her knowledge of graph theory to determine when each class will be offered. Since she is trying to make her students happy, Mrs. Jacobs does not want to offer 2 different classes at the same time if there are students wanting to take both. She decides to construct a graph in the following way. Each class is represented by a vertex, and if there is a student interested in 2 classes, those 2 vertices are connected by an edge. Alright, so suppose there are 5 classes, A, B, C, D, and E, only 5 students wishing to take the following classes. So we have Jason wants to take A and E, Emery is taking B, C, and E, Felicity wants to take A and D, Jeff is taking B and C, and then Hillary is taking D and E. So construct the graph for the principal. So the vertices are the classes. We're going to draw an edge if a student wants, between 2. If a student wants to, is interested in more than 1 class. Okay. So see if you can construct that graph. I'm going to pause the video. Let you come back. Okay. So your graph might look something like this. I have my 5 classes, A through E. Jason wants to take A and E, so I need to connect those 2, A and E. Emery wants to take B, C, and E, so those 3 need to be connected with a triangle. I want them all connected to each other, so B and C and E all connected to each other. Okay? Felicity, A and D, so I drew a line across here, A and D. Jeff wants B and C, those were already connected because of Emery. And finally, Hillary wants to take D and E, so we connected there. So that actually made a second triangle of A, D, and E. Okay? So let's see what we're going to do with this now. Number 11 says, find the chromatic number of the graph and color the graph using the least number of colors. So what's the least number of colors we can come up with here? All right, least number of colors. And go on, color the graph with those colors. So since we use letters for the vertices, we might use numbers for the colors here. Unless you want to use actual colors, that's fine too. All right. When you're done with that, number 12 then says, how can that help the principal with her scheduling problem? How will this help her with her scheduling problem? All right. We'll pause the video, let you work it out. Okay. So here's how I colored my graph. I actually started with EBC. I knew that that was a triangle. They had to all be different colors. So I said, I'm going to make E1, B2, C3. All different colors there. Then I have another triangle with EA and D. Well, A does not touch B or C. So it has to be different from E, which is 1. So I made A2. And then D, I made 3 also. So again, I have 1, 2, and 3 for EAD. Really, you could have made A and C the same color and B and D the same color, but I ended up with A and B the same color and D and C the same color. So then the question comes, well, how does this help us? On number 12, so our chromatic number here, let's start with that. Chromatic number is 3. We can get by with 3 colors. Okay? So how does that help us? How can the graph coloring solution help the principal with her scheduling problem? Well, each color is a different time, right? If it's connected with an edge, it has to be at a different time because that means somebody wants to take class at the same time. So E can be by itself. It's going to be at one time. A and B can be at the same time. C and D can be at the same time. All right? So I said, all right, I'm going to make E at the first slot. Let's just say 9 o'clock. A and B are together. They're going to be at my second time. Let's call it 10 o'clock. And then C and D, that's my third time. I'm going to call it 11 o'clock class. All right? So now with that schedule, every student will be able to attend all the classes they want. You have no issues there. Okay. So here's what you're going to do for the practice today. You're going to do this chemistry part right here. Okay, on number 13 here, you're only looking at the chemistry. Okay? It says certain chemicals cannot be stored with other chemicals. For example, to answer the question regarding how many storage facilities are required to house the following chemicals, graph coloring can be helpful. So we have 7 chemicals here. We know which chemicals cannot be stored together. So 1 cannot be stored with 2, 5, and 7. 2 cannot be stored with 1, 3, and 5, etc. It gives you all the information you need. So you're going to make a graph, 7 points. Connect edges to the ones that cannot be stored together. So 1, and let me just point out here, 1 can't be stored with 2, but that doesn't necessarily mean that 2 and 5 have an issue, although it turns out that they do. But like 5 and 7 are okay maybe. Well, no, they can't. But 2 and 7 are okay. Okay? But you guess 1, 2, 5, and 7 does not mean that all of these have to be connected to each other. 2 and 7 are okay together. All right? So make a graph, 7 points. Connect the edges of the ones, that cannot be stored together. And then your chromatic number will be how many storage facilities you're going to need. All right? And so what I'm going to ask you for the practice today, I want you to, in your answer, you're going to say storage facility 1. And you're going to tell me what goes in there. Maybe, 1, 5, and 6 or something. I don't remember what the answers are. All right, storage facility 2, and however many you need. Maybe you need 3, maybe you need 4. I don't remember. All right, however many storage facilities you need, tell me how many you need, and then which chemicals go in each one so that we are safe, so that, the things that are combustible together are not going to be stored together. All right, good luck with that. Do your best. And if you have any questions, get in touch with me. I hope y'all are doing well. It's Friday, so enjoy your weekend. We'll talk to you later. Bye-bye. All right, so that was today's lesson. See if you can figure out the chemical storage facilities and put your answers into the practice that I have there, the practice link that I have on Schoology. Okay? Have a good weekend, and we'll see you next week. Bye-bye.